Good afternoon, everybody. On day 3, session 7 of ATAL FDB, Bridging Academia and Industry, a NEP-Centric approach to AI, Robotics and Industry 4.0, 5.0. I welcome you all. Today our speaker is Dr. Sharvani Roy. Dr. Sharvani Roy is a professor of the Department of Computer Science and Engineering at Jadavpur University, Kolkata. She obtained her intake in Computer Science and Engineering from the University of Calcutta, India in 2002. She received her PhD in Engineering from Jadavpur University, Kolkata, India in 2008. She was awarded the Fulbright Senior Research Fellowship in 2013-14 and joined the research program at the University of North Carolina, Charlotte, USA. Her research interest includes AI for social good, IoT cloud, geoinformatics and data science. She was published in SCI journals, including IEEE and SCM transactions, scientific reports, Nature and the conference in reputed international venues. She has co-authored one book, Building Wireless Sensor Networks, Theoretical and Practical Perspectives, CRC Press. She has received project grants from MOE STARS, ISRO, DST, NGP, the Government of India and DSTBT, the Government of West Bengal. She has been involved in technical program committees and organizing committees for many international conferences. She is a senior member of IEEE, past chairperson of IEEE Computer Chapter, Kolkata section, and member of ACIL. Now, on behalf of the organizing committee, I request that our Honorable Vice Chairman and Director in Charge, SK, to felicitate our ma'am. Now I'd like to request our convener sir, GC sir, to felicitate Asif Iqbal Bidda. Next, I would like to request our co-convener sir, Aditya sir, to felicitate Shaunak Banerjee. Now I am requesting Dr. Roy to share her knowledge and expertise with us. Thank you and over to you, ma'am.
Thank you, Shaunak. Thank you so much for having me here. I hope I'm audible, right? So if you face any problem in hearing me, just tell me. I will try to. Is it required or not? I think it's fine. Thank you. So the topic is cloud computing as the foundation of Industry 4.2 and 5.2. So actually, two keywords are here. One is the cloud computing, and another keyword is industry standard 4.2 or 5.2. So we need to understand what is the requirement from industry and how cloud computing well suited or well fit there, right? So I try to organize my talk in that manner.
Abhishek sir.
I try to highlight
Abhishek sir.
the importance or the main features of Industry 4.0 and 5.0 and the key things about Industry 4.0 and 5.0, and then I try to highlight the basic foundation things about the cloud computing. After that, today I'm going to proudly introduce two of my research scholars, Asif Iqbal Midda. He is also a senior PhD scholar, net chair of our Department of Computer Science and Engineering at Dalipur University. He will talk about some standard cloud service providers like AWS. It would be nice if it's possible to share that knowledge using a hands-on, but you know, to experience AWS, we need to log in there, or you need to give some credit card information and that to some time. So he actually, as we already have one account, he actually logging in that portal and try to organize his talk so that you will get an idea of how to use AWS and the cloud perspective of it. After that, I have another research scholar, Shaunak Banerjee. He is also the lecturer of our department, and he is also working in the cloud computing related research. So we will talk about one or two topics that we have published recently on that research program. So our idea is to share our knowledge about the basic fundamentals of cloud computing and then its real presence in form of AWS and then some research topic. So before going to start the technical things, this slide, I don't know how much it is visible. In this slide, we are showing the trend of these topics. So that one is cloud computing, then here is the IoT, Internet of Things, and then these two are the Industry 4.1, 4.2 and 5.8. Looking at this trend, one thing is very clear, that people are really very excited about cloud computing, IoT and its industry evolution, 4.0 and 5.4. I don't have any slide on the AI trend. I mean, AI trend is also very encouraging one, like this 4 topics. Now, what is this industry standard? We are using this term Industry 4.0 or the 5.0. What is that actually? So it's nothing but an evolution. So if we look at the first such type of revolution in the industry domain, around in 1780, it was like Industry 1.0 that was mainly based on the mechanization, like railway engines, like that kind of revolution. Then in almost 100 years, after 100 years, 1870 around, there was the next that kind of revolution, that was the electrification in industry field, 2.0. Then in 1970, the industry was like automation. And then in 2011, it was like digitization. So if you can see that it started from, 1780, and those evolution was like 100 years apart almost. But in the last few decades, this was very quick. That means in 2011, it was 4.0, and within the next decade, 2020, is in 5.2. So we are really now citizen of a very fast moving era. Almost every decade, almost after every decade, we are having very rich experience with the technology engineering perspectives, right? So, what is Industry 4.0? Industry 4.0 mainly talking about the most popular technologies in the last decade. All of you know about this IoT, Internet of Things. What is the meaning of IoT? Internet of Things. That is simple looking things. It could be anything like a water bottle, this table, this chair, anything could be thing, right? But that is a usual thing. It's not a smart thing. So if you put some sensor on that thing and try to make it a smart one, and then if you connect that with internet, and if you connect so many such kind of things, then it's nothing but an Internet of Things, right? Why this kind of things are important? Because they are very useful in providing smart environment, a very good quality of life, and very ease in the environment, right? So that is Internet of Things. And when that concept, Internet of Things, adopted by any industry for industrial perspective, it termed as Industrial Internet of Things or IIoT. Then comes the cyber physical system. There's a little bit confusion with this two terms from the application point of view that IoT and CPS, cyber physical system, it seems like both are pretty much same. Actually, somewhere there is a similarity in both the fields. But in cyber physical system, two key things are very important. One is the cyber, that is the digital space, and another one is the physical, that is the physical space. So it's actually a very nice connection between the physical space and the cyber physical space, and these two things linked with each other and providing a very automated environment, a very smart environment. So somewhere you will find that there is a similarity or there is an overlapping between the technologies of IoT or IIoT and the system, and that is actually true. Now the third important or key technology is the artificial intelligence, and definitely at the present scenario with the popularity of AI, data science, and the demand of smart environment, the demand of high quality of life in terms of smartness, these all things possible with the help of excellent data analytics if we have. And that data analytics can be possible with the AI approaches. It's a very big subject, but it's termed as an artificial intelligence. There is this concept of machine learning, deep learning, probabilistic analysis, many things are there, but that is mainly to make a decision system a very efficient one, right? So that is another key technology there. The fourth one is the big analytics, big data analytics. Data analytics is good. We can understand the importance of data analytics because when we have this concept of IoT, we have this concept of cyber physical system. We are talking about making the environment system a very smart one. How it is possible to make a system a smart one? We definitely need something to study or to monitor the environment, and we definitely need to act upon it, right? So how to monitor an environment is possible with the help of sensors. So if you deploy sensors, if you put sensors to monitor the environment, those sensors are actually sensing the environment, they are collecting the data. And the data, if you look at the data, when you are monitoring an environment, is actually kind of a continuous monitoring, maybe periodical also. But just to understand the concept, think about a continuous monitoring environment. So continuous monitoring environment means a time series data. And now if you monitor it for a long period of time, the time series data, the size of the data will be very high, right? And when you have that for a very, very long period of time, it will be really very big, right? Moreover, the data is not coming from any one sensor, any one type of sensor. It could be from many different types of sensors, right? It could be text, it could be image, it could be numerical value, it could be audio, video. There is no restriction over the type of the data. Every type is important, right? If you have that. So this heterogeneous type, this multimodal sources, this lot of complexities, the whole thing makes it a very challenging environment. So when we have this type of situation, this time series data or maybe the spatial data, whatever the type of the data, and for a long period of time, it's usually with that's complexity of heterogeneity, multimodal, and different things. We need a very efficient or systematic approach to extract or to infer the knowledge out of it. So simple data, I mean the traditional data science approaches that will not fit there. That's why we need efficient environment so that it can address the challenges of that modern applications, and that particular field is nothing but the big data analytics. With the volume, veracity, velocity, all these properties are there, right? The last one is the cloud computing. And now how and why this cloud computing is see, before the smartness, before the smart environment or smart city, before that smart part, in 1980s or 90s, those who were the kids at that time, they know very well that internet was not very much there, right? It was started at the end of 90s, at the beginning of 2000, the access to the internet. But before that, there was no such huge access to data. There was no such application where we need to process that huge amount of data. But data was still there, right? Now with the popularity of internet, with the evolution and advancement in mobile technology, cellular technology, and later on in the last decade, with the popularity of smartphones, or the handheld devices which are equipped with sensors, we are the source point of this huge data, right? Now, if you want to build some application which are based on this access of data, you need an environment where you can store those data, where you can provide the computational facility to that data, right? So this storage, computation, these things are the infrastructural requirement. Usually, we have access to these infrastructural things in a limited manner. All of us may have one or two computers, desktop, laptops, mobile phone, all these things, but they have some limited amount of resources, isn't it? But when there is an increase in the data, that limited access to the resource is not sufficient. We need some way, I'm using the term knowingly, infinite access to storage and computation, right? That is actually provided by the cloud computing. And this is known as on-demand access to computing resources and data storage. Okay? So in this way, in Industrial 4.0, all these technologies coming together, right? Why? To provide solutions which are good for industry, which are effective for the industry, and as a whole for the world. Next, the benefits of Industry 4.0. I'm not going to spend more time in this particular slide. We all can understand that it will help us to increase the productivity. It will definitely going to improve the efficiency. Will gives us enhanced quality, greater flexibility, and different type of new business models. Why? Because we have the support of huge amount of data. We have the support of very modern communication technology. We have the support of modern sensor technology. We have the support of AI and predictive analysis to infer or to extract knowledge out of that data. We have the support of modern computing infrastructure facilities provided by cloud. We also have the support of excellent programming models to build web application, mobile applications, and all those things, right? So it's quite easy to understand that with the support of all those technologies, we can achieve these properties, which are definitely in demand. Now, in this decade, we are doing this new evolution of industry, that is Industry 5.2, right? So, I think we are still in Industry 4.0 because in the last decade only we heard about this technology advancement, and we are trying to cope up with this technology advancement. It's not enough time to understand all this technology, but in the meantime we reach to the next iteration or next evolution of industry, that is Industry 5.2. So what is new in the Industry 5.2? Industry 5.2 heavily dependent on top of Industry 4, right? So it is also using all those technologies that we mentioned earlier. Beside that, there is this human-machine collaboration. That means there are several sectors in industry where people are trying to build applications where they are trying to involve robots, they are trying to involve machines as much as possible, and they are trying to put more trust on building solutions where human and machine can collaboratively work. So this human-machine collaboration is one very essential or effective part of Industry 5.2. Then the sustainability and social responsibility. Now people are also looking at solutions which are sustainable, which are climate friendly, because climate related things are major issues in the present scenario. We are talking about the AI models, we are talking about the high-end computing infrastructure, but when behind those infrastructure, behind those technologies, there is a huge amount of things which are actually affecting the environment and the climate in a bad way. So people are trying to look into that also. They are trying to build solutions which are not harmful for the environment. Sometimes we are building AI model, and when we are trying to train them, it takes a lot of computation resources. It's generating a lot of heat, it is generating a lot of pollution footprint, right? Which is not good for the nature, which is not good for the environment. Now we are trying to build some solutions which are not harmful for the environment or the nature or as a whole for the climate. So here the focus is more on the environmental impact. So they are trying to build sustainable and social, keeping the social responsibility in mind. The last one is the customization and personalization. That is another aspect of the modern era. We all want some solutions which is very customizable. It will be work according to my choice, my interest, my way of living, right? And that will be useful to improve the quality of living of an individual, right? Like we are using the smartwatch. We are using smartphone apps which are good probably to monitor our health condition or something of our interest. Maybe the application which is running in your phone is not running in your colleague's phone, because your interest, your choices are different. So customizable solution, these things are now coming into the picture. Personalization solutions. So these are actually the main key points in Industry 5.2. Now we'll move to the cloud computing topic, but at this point we need to understand that how cloud computing is related with this evolution of Industry 4 and 5. right? So here the thing is, in this evolution of industry perspective, two things are very important. One, the infrastructural requirement, that is computation and storage, huge amount of computation, huge amount of storage, that infrastructural requirement is there. Second is, when we have this kind of environment, we also need solutions that can solve the problems and that can be run on top of that environment, right? So cloud computing solves these two or many such issues. I'm highlighting these two issues at this moment of time, but there are many such issues. So cloud computing is addressing those issues. Now, what is cloud computing? It is a definition kind of thing which is very commonly available if you Google search cloud computing. You will find Wikipedia, you will find some white papers where they define what is cloud computing. I'm trying to explain this by picking some of the keywords of this definition. So in this definition, it is like cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources like network, server, storage, etc. that can be directly provisioned and released with the minimal management support or service provider interaction. What are the keywords here? What we need to understand, what we need to remember. First thing is shared pool of configurable computing resources. So what is shared pool of resources? That means some resources are available, computation, resource, storage resource or any other kind of resource that is configurable in nature. Configurable means whenever I need that resource, whatever amount of resources required, that we can set before. That is configurable. And this shared pool, this pool of resource is actually shared. That is another very important thing. That means this can be shared by many users, many consumers. Right? So key points are mentioned here like on-demand service. So if there is a demand of any service, the service in terms of computation, storage or any other service that can be provided to the consumer or the user on demand. That is, if there is a requirement, then that can be provided to them. Broad network access. It is possible if everything is connected with a very nice and good network. Right? So, broad network access is the next point. Then the resource pooling, that is a pool of resources, computation, storage, all these things. Rapid elasticity. That means, suppose you need, say, X amount of storage at this moment of time for a particular application. And say after 10 days, you have more data for that application, so you want to increase it. The limit of the storage you want to increase. So if it is finally done by the service provider, then it is good for you. And if you don't need that amount of storage, if you want to reduce the size of the storage, then also if it is finally done by the service provider, then it is good for you. So that is nothing but the elasticity, but the nature of the elasticity should be very rapid. Very quickly. Why this quickly? Because here everything is pay as you use based on this model. That is, whatever resource you are using, you have to pay for it. So people don't want to waste their money, right? So if you are acquiring something which is more than what you actually need and you are paying for it, it's not a good thing, right? So you will definitely try to keep it within a particular level which is actually required because you have to pay for it. And there is this measured service, that means it is a measured metering. It is measuring your use of that particular resource, and based on that it is charging to you. Okay? Do you have any question there? Do you have any? No? Shall I move to the next part? So, in the next slide, I have mentioned some of the features of cloud computing. The first one is the multi-tenancy. Multi-tenancy means multiple things or multiple resources are part of that pool, and those resources can be shared by multiple users. Two important aspects is there. One is the total cost of ownership. This is from the service provider or resource provider point of view, because when the service provider is providing some resource to you, it needs to acquire that resource, right? So some investment is there, right? And now the service provider or resource provider will also make some profit from this business, because it's nothing but a business model. Cloud is not for generosity, it's not for helping others. It's not about that. It's a complete business model. So they are investing here to make some profit. So total cost from the ownership, that will be reduced, and then the provider's point of view, and total cost of provision. That is, when as a user you are paying for it, and you have this facility to over provision or under provision, as well as you have this access or facility for the elasticity, so you can increase or reduce the resource requirement as per your usage. From that point of view, there is this total cost of provision. So both service provider and service consumer point of view can be captured, well implemented with the help of multi-tenancy. Then there is this agility. It's a rapid, inexpensive re-provisioning of resources, because as a user you may want to re-provision it. At the initial point, suppose you don't have much idea about your application requirement and you are acquiring say X amount of storage. But later on you have decided, no, I don't need X, maybe it is X dash, where X dash is less than X. So that provisioning thing can be very rapidly happen. And that property or feature is known as the agility. Then comes the pervasive. Pervasive means accessing resources anytime from anywhere. From any location you can be able to access that resource at any time. Elastic, as I mentioned already, and pay per use. So this is actually the model of cloud computing, or the main features of cloud computing.
Madam,
yes.
you already said that the data is shared through the network.
Data is not shared. Resources are shared, not data.
Data is shared.
Definitely not. Your data is your data, my data is my data. I definitely
No, when
never.
I am stored the data in cloud, so that data is shared through.
No, definitely not. Data is not shared. Okay, I will explain. Yes.
Madam, then can we consider Google Drive as a part of this cloud computing?
Definitely, Google Drive is a part of cloud computing. And let me explain your doubt with this example. So, what happened in the Google Drive? You have a Gmail account. You get the access of the Google Drive. I am also having a Gmail account. I am also getting the access of the Google Drive. We don't have no idea where our mail boxes are stored, in which data center, from which data center we are getting the space or the storage of Google Drive. We don't have no idea. That is a part of the Google service provider. Service provider can have a physical machine, physical storage part, where it can allot a space for you in the same physical machine and a space for me. We don't have any idea where it is. It may be in the same data center, in the same physical machine, or maybe in some other data center, in some other physical machine. But we don't need to bother about that, because you will never be able to access whatever data I have stored in my Google Drive, and I will never get the access to whatever data you have stored in your Google Drive.
But data is stored in a physical location.
in physical machine.
So, what is
But that is not shared.
That is not shared. So they are not following the distributed database management system or what?
Definitely they follow the distributed system and distributed computing. Definitely they follow that. But when you are saying that my data is shared and that, but it means that anybody else can have the access to your data. That is not right.
That is not right. But
Resources are shared.
Resources
Are shared.
Actually, there in the data also there are some concepts that is called SAN, NAS, like that concept, storage area network, like that their data storing into hard disks there.
In any physical machine.
In
any physical machine. But there are different layers. I mean, very important here is to understand that the resources are shared, but it doesn't mean the content stored in that resource is shareable. Data is stored in some, say he mentioned that hard disk. It is shared in the hard disk, right? That hard disk is shared by multiple users. But that doesn't mean any user can access your data, right?
That is, we have a
For example, let me give you another analogy for it. Suppose in your office space, you are sharing the workspace with your colleagues. Say some room like this. And you have 2 almiras there with the lockers. Suppose you have 10 colleagues sitting in that room, and in that almirah you have 10 lockers. Every locker allocated to 1 faculty. So all of you are sharing that almirah. But any colleague of you cannot access your locker.
Yes.
That is kind of an analogy. Okay? Next, evolution of cloud computing. This is the theory from the computing point of view. Is not something very new. In 1960, John McCarthy, he brought up this concept that computation may someday be organized as a public utility. Now, what do you mean by public utility? This electricity is a public utility, right? Water network, the water we are using, that is a public utility. So these are the public utility. I mean, 1960, just imagine, just try to understand the vision of the scientist. He thought that this computation may someday be organized as a public utility. আপনারা সবাই বাংলা বোঝেন? আমাদের ছোটবেলায় কোনোদিন ভাবিনি, মানে আমাদের বাবা-মারা কোনোদিন যখন ওই মানে সংসারের খরচ কি হবে, টেলিফোন বিল ধরা থাকতো, ইলেকট্রিক বিল ধরা থাকতো, কম্পিউটারের বিল হতে পারে, এটা কোনোদিন তারা ভাবেনি। বাট আই এম শিওর যখন আমরা এই ব্যাপারটা ক্যালকুলেট করি, আমাদের বলতে হয় যে ডেটা কানেকশন কত টাকা, right? Internet bill কত টাকা দেবো? So that is actually the chain. Now this computation or the communication rather, these things are the part of the utility, right? So cloud computing turns computing into fifth utility. কিভাবে? We all are using smartphone. It doesn't matter whether you understand cloud computing or not. Your elder parents, those who are using smartphone, are actually using cloud computing. In every smartphone, you will find that there is a cloud app. MI Cloud,
Yes.
iPhone iCloud, right? Different type of cloud facilities are there. So it doesn't matter if I am cloud buji ki buji na. I am actually using the cloud. We are actually using the cloud. So definitely it's in the present scenario it becomes a utility. The evolution. খুব বেশি সময় নেই, খুব ডিটেইলে বলতে পারছি না, just in the present scenario where we are using the cloud, একটা জাম্পে আমরা এখানে পৌঁছাই। It was a lot of evolution, lot of paradigm shifting. Initially it was started with the client client-server paradigm. Client-server paradigm was the first that kind of paradigm. After that, there was a P2P computing, peer-to-peer computing. After that, there is a cluster computing. You have some number of nodes, just create a cluster and utilize that as a computing, cluster computing. Then, at the end of, not at the end of, at the middle of 2000, around 2003-4, there was one scientist, Ian Foster. He come up with this idea of grid computing. Grid কথাটার মানে হচ্ছে, let me give you another analogy that suppose you want to switch on this light. This one is not on, so you want to switch on this light. You are pressing a switch, right? And this will be lit. You are not bothered about from where this energy is coming. From where this electricity is coming, we are not bothered about that. It can be coming from anywhere. In our country or in many other countries also, there is a grid network, grid to provide electricity, right? So the grid term comes from that. Grid computing means every computational resources will be connected to the grid. If it is possible, and if a user requires some computational facility, they can easily use it. They don't need to bother whether I have that or not, whether I have that resource or not. I need that resource and I will get the access of that resource. That is the simple philosophy behind grid computing. যেভাবে আমি ইলেকট্রিসিটিটা পাই, কোথা থেকে আসছে সাউথার্ন দিকে, সাউথ এখানে একটা আছে না সাউথার্ন, তারপরে এনজিপি, NGP character. So there are many points from where this energy sources can reach to this point. But we are not bothered about that. So that was the philosophy behind grid computing. I did my PhD in grid computing, but after that, what happened? In grid computing, the main focus of the research was on this objective of providing computing as an utility service to the consumers or the users, right? Money was not involved there, right? So this giant companies like IBM at that time, Microsoft, Yahoo, all they were big giant in this computing business. They have huge resources. So they thought if anybody need computing as a service, they will provide it. So they come up with this approach of pay and use model. Pay and use model with that philosophy. So utility and then pay and use model, this thing is the, what happened to this? This thing is the grid computing. So after the grid computing, the pay and use model adapted, and then the modern days cloud computing. The philosophy behind grid computing was also focused on utilization of the resources and flexibility of managing the resources. These two key parameters are still the main focus of the cloud computing, but with that pay and use model. Okay?
Ma'am, I have a doubt. This is the only difference between grid computing and
No, not only differences. This is actually evolution, technological advancement. As per my knowledge and my understanding, it is hugely driven by the giant companies. Why giant companies? Because they had that vision of converting it to a business. If you go by the philosophy of grid computing, it is all about providing that service. It is not about any business. But in cloud computing, the aim is same, but it is equipped with a business model. Why I am saying that? Is it ক্লাউড ইউজ করি কি লাগে ক্লাউড ইউজ করতে suppose you are taking the pictures and from your phone you are sending those pictures, you are pushing those pictures to some cloud storage. So cloud storage is nothing but some remote storage, some remote server, pushing a file from your computer, your device to remote device. What you need?
Internet.
That is from the connectivity point of view, from the programming paradigm point of view. What programming paradigm you need?
Interface.
Client server programming paradigm. Very simple client server programming paradigm. আমরা যখন অপারেটিং সিস্টেম করি অপারেটিং সিস্টেমে আমরা SSH করি টেলনেট করি বা পড়াই what is the concept of that? Getting access to some remote
machines.
তাহলে ওইটা যদি হয়ে যায় you will get the access তারপরে ওইখানে গিয়ে রাখা তার ইন্টারফেস these things are the part of the development. Challenges are definitely there. Challenges, I mean, if you look at the challenges of grid computing and cloud computing, you will find a very good significant overlap of that. The objectives, you will find a very significant overlapping in there. কিন্তু grid computing হচ্ছে সেখানে ওই মানে পি এন্ড ইউজ মডেলটা কোনোভাবেই ছিল না। আরেকটা অন্য একটা অ্যানালজি দিয়ে এভাবে বোঝানো যায় যে জমি রয়েছে চাষের, ঠিক আছে? যদি মডেলটা এরকম হয় যে যে চাষ করতে চায় সে ওই জমিতে গিয়ে চাষ করবে, কারণ একজন যে চাষ করবে তার কি চাই? তার জমি চাই, জমি আছে এবং যদি আমি চাষ করতে চাই আমি সেখানে গিয়ে চাষ করব। এটা একটা মডেল। আরেকটা মডেল কি? জমির কেউ মালিক আছে, চাষ করতে চাইলে ডেফিনেটলি চাষ করতে পারো, কিন্তু তোমাকে এটার জন্য সেম থিং। তাহলে এবার যদি আপনি বলেন যে দুটোকে একেবারেই সেম না, কোথায় আলাদা? এবার চাষ করতে হলে কি কি করতে হয়? দ্যাট পার্ট ইজ সেম। অ্যাক্সেসটা পেতে হবে, তারপরে তো হঠাৎ করে ক্লাউড কম্পিউটিং হয়নি, তার আগে ক্লায়েন্ট সার্ভার প্যারাডাইম ছিল, তার মধ্যে SSH, রিমোট লগিং, টেলনেট, অল দিস থিংস ওয়্যার देयर। ডেটা ইন্টিগ্রেশন সেটাও একটা থিওরি আলাদাভাবে তৈরি হচ্ছে, বিগ ডেটা অ্যানালিটিক্স এগুলো তৈরি হচ্ছে, অ্যানালিটিক্স ইন্টারফেস, ওয়েব ইন্টারফেস, অ্যানাদার ভেরি ইম্পর্টেন্ট পয়েন্ট হিয়ার ওয়েব পয়েন্ট 2 তার উপরে বেস করে, কারণ এভরিথিং ইজ কানেক্টেড ইন ইন্টারনেট এন্ড উই আর অ্যাক্সেসিং দ্যাট থিং ভায়া দ্য ওয়েব প্রোটোকল, রাইট? সো এটা ডেফিনেটলি দেয়ার। আই এম টকিং দিস ফ্রম দ্য ফিলোসফি পয়েন্ট অফ ভিউ। আমি ওইটাকে একটু হাইলাইট করে
মানে
বলছি।
টেলনেটের কনসেপ্টটা তো আমার গ্রিড কম্পিউটিংও লাগছে,
টেলনেট যে কোনো রিমোট অ্যাক্সেস,
যে কোনো রিমোট অ্যাক্সেসই লাগছে।
এই যে কথা বলি, এই যে ক্লাস্টার কম্পিউটিং, দিস ক্লাস্টার কম্পিউটিং কি হয়? ক্লাস্টার কম্পিউটিং এ সাপোজ ইউ হ্যাভ ইন ইওর ল্যাব 30 computers, 30 people can sit on that computer, they can use that. Suppose you have a very computer intensive task and you need the power of 30 processors. For the simplicity, let's assume that all those computers are single processor computers. But you have a compute intensive task which requires 30 processors. If you want to purchase a 30 processor system, heavily পয়সা খরচ করতে হবে। But as a computer science enthusiast, what you can do, you can simply build a cluster computing environment with those 30 computers. That will give you a distributed computing environment, and if you are a very good programmer, you can run your application in such a manner so that it can exploit the resources of that environment. 30 computers এর যে ক্লাস্টারটা রয়েছে সেটা এক্সপ্লয়েট করবে। এই কাজটা যখন আমি ক্লাউডে করতে যাচ্ছি, ব্যাকগ্রাউন্ডে কিন্তু এই 30টা প্রসেসর নিয়ে বা যা রিসোর্সেস ছিল সেটা তার ডেটা সেন্টার, তার ফিজিক্যাল মেশিন রয়েছে। It is giving you that interface, it is giving you that access to the framework where you can write your application in that manner and you can run your application to exploit that resources. Okay? Okay. Now I'm moving to some perspective of cloud computing. Two things are important here: capacity versus utilization. খুব কুইকলি এই জায়গাটা যাবো কারণ টাইম একটু লিমিট আছে। What is capacity? Suppose there is one company that want to start its business, and that company has some estimation over the capital expense to start its business from the computing resource point of view. So this is say the estimation, right? So this estimation, looking at this diagram, we can easily understand that with time there is an increase, right? So suppose that company started with some resources by spending this capital expense, right? Now there is a high demand. This capital expense or this computation is not good enough to fulfill the requirement of this company. There is a increase, right? So in this situation, this is called traditional infrastructure model, where the company need to invest again it need to invest in this amount. Now do you have any idea what this particular section is meaning? What is the meaning of this particular section? Here the forecasting was like this. It has invested and it has this resource, but the demand was up to this, so this there is no use of it, unused, right? And so on, right? So this is a traditional infrastructure model. So that is an acceptable surplus. You have to accept that surplus. That is a surplus and acceptable surplus. But in reality, it is not that simple. The first thing is that it is not linear in nature. It could be something like this, right? If it is something like this, sometimes it is surplus, sometimes there is a deficit, right? So that is surplus, there is a deficit. Now, the property of a good infrastructure model will be something like that. Whenever there is a rise, it will fit that. Whenever there is a down, it will also fit that. A flexible solution, right? Now, if we combine all of these things, we will get something like that. There is this dotted line is the predicted demand, but the actual demand is shown here by this red line. Then there is a scale up. What will you do? As there is a fluctuation in the demand, you can scale up, and if you follow the scale up approach, then you have to address too much of the capacity and you need to invest huge capital expenses, right? Then if you follow a traditional scale up technique, sometimes you acquire something, then you lose that and acquire something. Then also at some point you may have a very high capacity. What should be the right solution? The right solution is shown here by this green line. It will be automated scaling as according to the requirement or the demand, right? যখন যতটা দরকার তখন ততটাই, বেশি নিয়ে লাভ নেই, that's the main thing. So that is actually provided by cloud computing environment. You need this amount of resource, you can acquire that and you can pay for that. That is the idea. In cloud computing, everything is represented in form of a service. There are two situations. One,
Ma'am, one question. In grid computing, everything was represented as a service. Same line.
no. In grid computing, it is not. I tried to highlight the grid computing, the concept of grid computing, to clear the philosophy behind it. What is the philosophy? What was the main objective or aim at that point of time? For example, suppose you have a computing device. Let me give you another analogy to get a more clear picture. You have a laptop. I also have a laptop. But say I am just using my laptop for email checking, and in a day I can do that 2 or 3 times. Rest of the time my laptop is idle. So the utilization of the resource of my laptop is almost
Zero.
But you are running a business and you need computation resource, say 10 or 15 hours in a day, right? And your own laptop is not sufficient, not good to fulfill that requirement, right? So is it possible to build an environment where you can get that resource, the amount of resource you need? That was the initial question. It is possible. If it is is possible to connect all these computing resources in a grid. Just like the concept of electric grid. There are many points from where the electricity generated, right, is generated. So if you connect everything in the grid, everyone can take that.
It is a part for sharing the resources.
It is the part of sharing
And
this.
cloud computing means storage plus
Cloud, no.
plus
Cloud computing is also about sharing the
sharing the
resource
resource with service.
in form of a service
Correct.
with pay as you use model. Okay,
Means grid plus pay equal to cloud computing.
not exactly.
Not like that.
Not exactly. But I'm saying that it's about the philosophy. It's about the philosophy.
Architectural model is different.
Definitely there is a difference. Definitely. Globus toolkit was a very popular toolkit for building a grid environment. And in the Globus toolkit, it was mostly focused on the web interface and the connection to the remote user to provide the users an environment where it can seamlessly get the access of the resource. Whereas in cloud computing, we have a very advanced web interfaces and most of the application with a very ease you can do. When you are pushing your say the photos or the any doc files to the drive or to the cloud, you don't need to bother much. But in the but in the grid computing, it was not that advanced. So with the evolution of technology and the web, all these things possible at this moment of time. On premises. So suppose if you want to build an say business, you need many services, mainly computing business say. So what do you need? You need networking facility, you need storage, servers, virtualization, operating system, middleware, runtime, data applications. You all know about these things, right? These are the part of any computing environment. So if you want to have all these resources on premise, you need to take care of all these layers. All these are your responsibility. Managing, handling, everything is your responsibility. Now what happened at the cloud? Cloud provides different service models like infrastructure as a service, platform as a service, software as a service. How these three things are different? In infrastructure as a service, you can see that the bottom 4 layers, that means the networking, storage, servers and virtualization, up to these blue mark things are managed by the service provider, right? And top of that, you can use your own operating system, middleware, runtime, data and application. So this is called infrastructure as a service. A good example of infrastructure as a service is AWS, EC2, Google Cloud Platform. So these are the examples of infrastructure as a service. Then platform as a service. Platform as a service from networking to runtime, that is including the operating system, middleware and runtime. All these things are managed by the vendor or the resource provider, service provider. And then you are only bothered about the data and application. This is platform as a service. Like AWS, Lambda, Google App Engine. These are the examples of platform as a service. And then software as a service. As a user, as a resource consumer, you don't need to bother about any of these things. You're simply using it and everything will be taken care by the service provider. So this is software as a service. So Google Drive, Gmail, Facebook, and these all things are the example of software as a service. Now there are different deployment models: private cloud, community cloud, public cloud, and hybrid cloud. So private cloud means it's private to any organization. For example, if this college, if this college has some resources and if it built a cloud, that will be limited to the stakeholders of this college, the users, could be the faculty or the students. So that will be private. Anyone outside of this college probably will not get the access of that. Community cloud means anyone can use it, yours, it's mine, but not his. Maybe some other party, it's not for them. And public cloud means it can be used by anybody, like who is willing to pay for it. So public cloud examples are like AWS, Google Cloud, Heroku, Azure, all these are examples of public cloud. And hybrid cloud is the some part will be provided by the standard service providers and some part will be private. For example, if your college wants to collaborate with AWS and if they have some private and some public parts, that will be a good example of hybrid cloud.
Can you say Google Docs is a software as a service?
Yes. Definitely.
But whatever facility we got in the Microsoft Office, all are not available in the Google Docs.
In the present scenario, Microsoft 365, I guess, Office 365, that is also as a software as a service. It's coming to us as a software as a service. So, real scenario of resource provisioning. Let me give another example. Suppose there are two companies, Blue company and Red company. Blue is having this type of requirement and Red is having this type of requirement. Say in this y-axis, it is showing the number of computers it requires. Say, for the sake of simplicity, so Blue company required 2000 computers and Red company required 2050 computers. Now, this is a timeline data. So now, the service provider, say the cloud service provider, with 3000 computers can fulfill the request of both these companies. But if you look at their demand, it seems like they need 2000 plus 2050, that means 4050 computers are required. Right? But in reality, cloud provider is providing its services with 3000 computers, but it is charging for 4050 computers and making some profit and providing resources to the user. This is called resource provisioning from the cloud service provider point of view. Cloud service providers are making profit in this, I mean, not exactly in this manner, but it will help you to understand the approach, right? There's another concept called quality of service. So everybody is providing some service and they need to maintain that quality of service. But in most of the time, there is a trade-off between the cost and performance. So they are charging something for that performance, and as a service consumer, we don't want to pay so much. So there is some compromise in the cost and the performance. So it's sometimes like a race to bottom versus quality of service. I'm skipping this part because we don't have much time. So there is this demand. If you look at this diagram, you will see that the demand is not very high during this period of time. But suddenly there is a huge demand. Again, if you look at this, you can see that there is no such demand, there is no very high demand, but suddenly there is a spike in request. Right? So at this period of time, the resource utilization will not be very high, but at this point, the resource utilization is very high. Again, there is no very high resource utilization. So when there is a high demand, you may need to scale up it. So that is the part of the elasticity. According to the old deployment, you probably have the access up to this, the marked by this dotted blue line. But as there is a high demand, you need to increase the resources. So there is a scale up situation, and the solid blue line is showing the new deployment. So sometimes there is a situation that available resources are not available. Suppose this is the actual resources and this one is the plan, and sometimes when there is a not a very nice relationship between the demand and the availability, so some unused resources may be here, right? Unused resources means wastage of resources, not a proper utilization of resources. So is there any way of managing that? There is a way that if you imagine a situation where you have different type of service provider, small and mid-sized cloud service provider and giant service providers like Amazon. So the mid-size or small service providers, they have limited amount of resources, like, right? But they are, say, in this business of cloud service as a cloud service provider. But the Amazon, Google, they have huge amount of resources and they have huge amount of request also. But if this two party, so there are actually two scenarios. One is the high demand, overutilized resources, more resources will be better. This is one situation. Another situation is when it is a very low demand, there is no much request, resources are underutilized, more requests will be better. So if two types of parties already exist in the environment, one has huge resources but no much request, one has more requests but no much resources. These two parties, if they collaborate, then they can make more service or more business, we can say. This collaboration is known as the Cloud Federation. Cloud Federation is still part of the research topic. It is not implemented in reality yet in a full form. We have some experience of working in the Cloud Federation. So it is something like that. Different service providers are collaborating and forming a federation. Different users are there. So there will be a broker. That broker can establish a handshaking between the service consumers and the service providers. Okay. So then I'm coming to this back concept of virtualization. Okay. So what is virtualization? All these things of cloud computing, that is based on top of this concept of virtualization. Virtualization means what? Virtual view of something, not in actual fact, right? So this concept of virtualization is nothing very new. It is not like that it started with this cloud computing, it is not the case. We have this concept of virtualization not in this form, but we have pretty much similar concept in operating system, in virtual memory, in CPU sharing, all these things. We have this, JVM, right? So all these things we have this idea of virtual or virtualization, right?
Hard disk is also.
Which?
Our hard disk is also virtual.
Yeah, that's why I said virtual memory. Virtual memory is actually the RAM, hard disk, all this, involving all these things, presenting the virtual of that. So here we have two situations. In this one is a physical machine where we have different type of resources like CPU, memory, network interface card, and disk. Say is part of some standard architecture, x86 architecture, and then there is an operating system layer, and then on top of operating system, any application is run. This is a traditional approach, a physical machine approach, right? So here we have only single operating system. Here we have a very tightly coupled hardware and software. This is very tightly coupled, and here one limitation is, the major limitation of this traditional approach of physical machine is that resources are underutilized, because only few applications are running on top of operating system, and probably the hardware resources have more capability to fulfill. So what is the concept of virtual machine now? The concept of virtual machine is, these resources will be here, that CPU, memory, disk, NIC, network interface card, all these things are there. And then there will be a virtualization layer. This virtualization layer provides different virtual machines. And on that virtual machine, we can have a layer of operating system, and top of that operating system, different applications can run. Right? So this is the idea of virtualization. This virtualization is also known as hypervisor or virtual machine manager, or VMM. The background of this virtualization or virtualizability was first explored by two scientists, Poppet and Goldberg, in 1974, they published one paper. In that paper, they mentioned about these three categories of instructions. The first one is the privileged instructions. The concept of privileged instruction is same as the concept of privileged instructions in operating system, where you execute some instruction in a more privileged mode, but will be trapped if required, right? Then there is this control sensitive instructions. What is the meaning of these control sensitive instructions? It's attempt to change the configuration of any resource if required. So these type of instructions are known as control sensitive instructions. And then there is a third type of category which is about behavior sensitive instruction. Those are special kind of instructions where they behave in a different way depending on the configuration of that resource. So based on this categories, actually sensitive, the set of the sensitive instructions and how those instructions can work on this mode of privileged instructions in hypervisor, and how the hypervisor intercept any instructions to trap it or to consider it as a privileged instruction. These things are the main theory behind the virtualizability or the implementation of the virtualization behind the task. In very simple words, to make a link it with the operating system concept, I can give you one example. Like in operating system, we all know about the system calls, right? So usually the system calls is something where it has the direct access to the hardware, and system calls is something when you have some part which are more privileged, and those more privileged calls can be implemented with the help of system calls, right? So those system calls, when you have a virtualization situation, when you have a virtualization layer on top of it, when you have a different type of VMs, and those VMs are actually using those hardware resources in form of a more privileged instructions that need to be tackled with the help of that VMM layer or the hypervisor. So that is the concept, theory behind the virtualizability. So this is an idea how this thing can be implemented. As we know that the CPU time can be shared among multiple processes in multi-programming or multi-processing concept. So here also different VMs can share their CPU time, and those time slices can again shared by multiple applications which are running on that VM. Okay? Now, different type of virtualization concept can be implemented. The first one, the very simple one, is known as the type 1 bare metal. What happens in this bare metal? If you look at this diagram, you have a hardware layer. On top of that, you have a hypervisor or virtual machine manager, and then you have the VMs placed on top of that hypervisor. So whatever application running on this VM, they can access the hardware resources via the hypervisor. So we don't have this concept of operating system here, but the role of making the system call or executing the system call or giving the privileged execution of the more privileged mode instructions or trapping the more privileged instructions, all these things are managed by the hypervisor. This is another representation which is known as a type 2 or also known as a hosted. So in this approach you can see that there is a hardware layer, there is an operating system layer, and that is actually the host operating system. On that host operating system you can place a hypervisor. That hypervisor will work similar like the previous one with having one or two virtual machines or more number of virtual machines, but this hypervisor works along with the host operating system. It is not that there is no host operating system, there is a host operating system, and this process can access the hardware resources via this OS, but the application which is running on top of this VM will access the hardware resources via the hypervisor. So hypervisor here can skip this OS for making the system calls and directly use of those hardware resources. Okay? So this is known as the binary translation or the full virtualization concept. I am just explaining this diagram so that you can get an idea of how this thing is implemented. From the operating system concept, you you have this idea of different rings, right? So this is the hardware on any host computer, and then there is this concept of ring 0, ring 1, ring 2, and ring 3, right? The ring which is very close to the hardware is actually able to execute more privileged instructions, right? On the kernel or the system call, all those things. So in this binary translation approach, you can see that virtual machine manager is placed in the ring 0. So you can directly use this hardware resources, or you can make the use of hypervisor calls. On top of it, in the ring 1 there is a guest OS, and in ring 2 it is there is nothing, and in ring 3 there is a user application. Do you have an idea what will be in the ring 2? Just from the OS point of view, it's nothing but the device drivers, right? So device drivers are some part which can be placed in the ring 2. So here you can see this user applications.
Then this is
that,
type 1 or type 2?
which one?
This first, what you are playing, that ring 2 is 0, vacant. Ring 2 is vacant, na ma'am?
Ring 2, yes.
This is type 1 or type 2? What for?
No, this is actually the virtualization using binary translation technique. And so the point here is, from the user application, if it got to make use of any hardware resource, it can make a hypervisor call in spite of system call that can be passed through the operating system. Here it is making a call with the hypervisor, and hypervisor is providing access to that hardware resource to that application. And the second one is showing the full virtualization, that is hardware assisted full virtualization, mainly Intel virtual translation, virtual technology, or AMD virtual technology. These things are implemented in hardware full virtualization technique. Here you can see that we have one extra ring, which is beyond ring 0, down there as a ring -1. And the virtual machine manager is placed in ring -1. And in ring 0, it is having the guest OS. Where ring 1 and 2, these two rings are blank. Any kind of device driver or any kind of specialized drivers can be placed here. And then in ring 3, it has this user application. So here it's quite obvious and it's very intuitively we can understand this concept, because in the full virtualization or hardware assisted virtualization, it's based on the hardware. It is managed and controlled by the hardware, right? So the VMM, that is virtual machine manager, need to be placed very close to the hardware, right? So that is the case over here.
Yeah, in the picture too, why there is an extra ring?
In this one?
Yes.
Yes, that's why I just explained it. It is actually hardware assisted full virtualization technique, adapted by Intel virtual technology or the AMD virtual technology. So here the virtualization concept is implemented very closely with the hardware, not the case of the first one where the binary translation happened, right? So if it is very close to the hardware, ring 0 is some place from where you can make the system called more privileged calls, right? And ring -1 is something where you have direct access to the hardware. That's why they have one.
Translation.
Huh?
There is no binary.
No, this one is not binary translation. This one is maybe hardware assisted, and this depends upon that architecture also. But Intel virtual technology and AMD virtual technology, it depends upon that Intel hardware, it depends upon the AMD hardware like that. Okay, so that's why it is in ring -1, very close to the hardware, right?
Madam, in Oracle VMbox, if I installed a software within a VMbox, then it will approach to the VM.
It is not like this actually. This will be something like this, or maybe something like that. This one, binary translation or para virtualization. Because you have a host operating system. Here you are installing a virtual box. So you have the hardware layer, then you have the host operating system, then you have the VMM, which is your guest operating system or the virtual box. Then on top of that, you are creating multiple VMs, right? So it is not very close to the hardware. If it is hardware assisted, it will be direct access to the hardware, like the full virtualization technique of Intel VT and AMD.
So ma'am, JVM is also used parallel virtualization.
No, the JVM idea is different from that. JVM is creating a virtual machine for whatever Java program you have written. It is in that form. It is not giving you the opportunity to create virtual machines. Several virtual machines are utilizing the hardware access for that. Okay, that concept is different from this concept.
Why then it is called virtual machine, not the physical machine? Because
A very good question. So basically, physical machine is what? Physical machine is whatever you have in form of a physical component. You have this amount of RAM, say 8 GB RAM. You have say this amount of hard disk. You have say 2 or 4 core CPUs or something like GPU or whatever. This is what you actually have. That is the physical machine. Virtual machine means what? Suppose I need one processor, say 8 GB, say 2 GB RAM and say X amount of hard disk. And your physical machine can provide it. He probably need a similar kind of thing and she also needs a similar kind of thing. Your system has all these things, right? So what you can do? You can create different virtual machines for our requirement. With the understanding that probably your resource will not be exhausted when fulfilling the requirement of the task submitted by this and this user. And it is possible because in multi-programming, multi-processing environment, what you do? The CPU is shared, the memory is actually shared by multiple processes, multiple programs. Here also you are sharing the whole resource by multiple.
okay, madam. Then that's why actually physical machine supporting the backbone of the virtual machine.
You can say that. Okay. So this is another para-virtualization technique where this is the host computer. You have a virtualization layer just on top of hardware. That was previously in ring -1, there is the virtualization layer. And then in ring 0, you have the para-virtualized OS, and in ring 3, you have the user application. So hypercalls to the virtualization layer actually replace non-virtualizable operating system instructions in para-virtualization. So it's almost 4. I think I should stop here. Otherwise, we will not get time.
No, madam. We do not have any problem for our end. Now usually, as you are staying very fast, so it's up to you. Otherwise, we have time to fix it.
Okay, fine. Let me discuss few more things, and you just plan what part you will discuss here and what part you will want to skip. So another point is, suppose you have a physical machine and you have some virtual machines running on that. Now there are some perspectives like load, performance, fault. These are few things that you need to take care of. For example, in this schematic diagram, if you can see that there are 2 physical machines, A and B. And in A, 3 virtual machines are running. In B, only 1 virtual machine is running. So there is no problem with this setup. Is there any problem in this setup? No. There is no such problem. But if you think differently, you will find there is some problem. What is the problem? The problem is this environment is not load balanced. This is not load balanced. So what would be the good solution? The good solution is if you can migrate one VM from this to this. Right? In this situation, A is running 2 VMs, B is also running 2 VMs. So this is called load balance solution. For this load balancing, what you have to do? You need to migrate VM. So that is another thing. VMs can also be migrated. It can be moved from one node to another node. This another example. When there are 3 computers, 3 physical machines. Every machine is running 1 VM. Is there any problem with this setup?
No.
প্রত্যেকে একটা করে ক্লাস নিচ্ছে। Load balance, perfect load balance. Underload এ আছি। So there is no such problem. Actually, the problem is with the administration. So this is the problem here. It is not a very energy efficient setup because you need to run 3 physical machines. So it is consuming the energy of 3 physical machines. Where you can migrate these 2 VMs to this one, and you can run only 1 physical machine. You can switch off other 2 physical machines, and you can save some money, you can save some energy. Though it's not good for us, but for computing world it is a good solution. আমাদের জন্য ভালো না, but this is a good solution, energy efficient solution. These are 2 examples where VM migration is required, right? And this concept is known as consolidation. Consolidation technique where this VMs are consolidated in this one. So there are some service providers like Amazon Web Services, Google Cloud Platform. They are providing virtual machine and they are providing cloud services. My research scholar Asif will talk about Amazon Web Service, and there are some problems with okay. So I mean, we are not linked with any business things, but we are wholeheartedly researchers. So we try to explore this subject from the research point of view, right? And I know that you people are also in academia, and you people probably also interested in research. So just want to highlight few of the research areas in cloud computing. It's from the basic concept of cloud computing, it's very easy to understand that there's a requirement of increasing adoption and growth of the resources and demand, utilization. Resource optimization is definitely one important part there. Automation, flexibility, sustainability, and customer experience. So these are some important research aspects in cloud computing. And there are some research areas in cloud computing where we are currently working. The first one is the workload modeling and forecasting. What is the idea of workload modeling and forecasting? My student Shona will discuss that. Resource allocation and scheduling, efficient placement, energy efficient consolidation. Energy efficient consolidation is based on the concept that I just discussed few slides ago. So I'd like to stop here, and I just want you to listen to my students. They will share their concept here. And for reference, I have mentioned some, 3 books are mentioned here, some tutorials and some blogs also
Madam,
here.
I have a question, madam.
Yes, please.
Madam, I found one slide, you have mentioned Docker. So if you get some little bit time.
He can explain it, but let me, as he is asking about that, let me just give an overview of this. So the idea is there is a physical machine. This is the physical machine, right? On top of physical machine, to improve the utilization of the resources, we have this idea of virtual machine, right? VM. So multiple VM can run here. Now VM is what? If you remember this layered architecture, VM is something where you have this hardware, you have a host operating system, on top of that you have this hypervisor, on top of that you have multiple VMs, and on top of each VM there could be a guest OS, and there could be multiple applications running. Now what is the problem here? The problem is these applications are sharing those resources, and they are accessing the operating system, its system calls, all those things, and different modules of the operating system. And when we are talking about this load balancing, when we are talking about the energy efficient things, we may need to migrate this VM from one point to another point. But by the theory of VM, or with a very simple understanding, we can easily say that VMs are not very lightweight things. They are heavyweight, and to migrate VM from one point to the another point is also not very easy task, right? Then comes this concept of container. In container, what happened? It will consider a significant part of the OS, or it's a binary image or binary representation of the whole thing, which is having the main modules, which are actually the main module of the operating system, the main module of the application libraries or any APIs, whatever it requires to run that application. Everything is in form of a container. So that is the idea of the container. Now to build this, so container, another very simple analogy is, suppose you have a very big building, say 20 floor or 50 floor building, there are multiple flats, so those are actually containers. And everything is hosted in a big building, which is nothing but the physical machine. Now, to develop a container, all that things in form of a package, so that you can move it from here to there, or you can run it in your desktop, laptop, or in the data center, anywhere. To bring that flexibility, you need a Docker environment. So Docker is providing that tools of that framework where you can develop it in form of a container or in form of a package. Once you have that package form, Docker is also implemented as a client-server programming paradigm, which has a Docker client, Docker server, registry services, all those things. And once you have that thing, you can move the container from one place to another. Then there is another concept of Kubernetes. Kubernetes is something where, say, in cloud, there is no downtime. It is always up. It is always alive. But in reality, if you think about it, it's not a very practical or it's a very realistic to have that strong, robust environment where everything is up at every moment of time. That means in theory, it is something where there is no concept of fault, there is nothing like fault, error or anything, right? But that is not possible. So in reality, fault will be there, error will be there, and downtime is also very obvious. But as a user, we are never facing any downtime, we are getting always up. How it is possible? It is actually possible, আরেকটা analogy দিচ্ছি, as we are the teacher, আমার জ্বর হলো, আমি ক্লাসটা নিতে পারছি না, আরেকজন আমার কলিগ সে ক্লাসটা নিয়ে দিলেন, right? So it is replaced, right? Here also, if one container is facing any problem, if one container is having any issue, fault or anything, it will be replaced by another container. This concept is known here as a self-healing. So this self-healing property can be implemented if you have that framework. That framework is provided by the Kubernetes. Kubernetes provides this flexibility, the self-healing, all these things. Okay. So roughly I AICTE bolla. Next, as I so these are some references. If you are interested, you can explore that to know more about this. Some of our research papers, and if you want to know more about our research or our research team, you can visit this jucells.org, and we also have started a YouTube channel called JUCells, and we are trying to create some videos related to the research work, related to the teaching learning, and not many, but some of them are already posted here. So if you are interested, you can also visit that, and please subscribe and follow our channel and our work. That will be very nice from our side also. Now I very proudly introduce my research scholar, Asif. He will talk about AWS.
Ma'am, I have a question.
Yeah, please.
What specific skills do you believe one should develop in the context of cloud computing?
Right. So for cloud computing, see, there is two subjects. One is the two subject. one is the distributed computing and another one is the distributed system. Distributed system talks about mainly highlight the system requirements, right? And distributed computing is covering the topics which are very useful to build applications that can run on top of distributed environment, right? So cloud computing is one significant part of distributed computing, right? So they need, I think, a fair knowledge about the distributed computing, distributed system, then cloud frameworks and programming paradigms like MapReduce, Hadoop framework, and the basic fundamentals of cloud computing like virtualization, VM migration, and what else? Container, the concept of Docker, Kubernetes, and at the beginning they also need to understand this evolution from client-server paradigm to P2P, cluster computing, and read computing, a little bit of read computing, and then the concept of cloud computing. Okay?
And what are the emerging trends that are going to shape the future of cloud?
Emerging trends will see these technologies are not a standalone technologies at the present scenario. As I told you, IoT, cyber physical systems, data analytics, data science, AI, big data analytics, cloud computing, all these things, even web development, mobile app, things are linked with each other. For example, if you want to develop some solution or some system as an end-to-end system, then you need to have a fair knowledge about endpoints. So what are the endpoints here? For example, let me give you this example of health monitoring applications. Many people use those health monitoring applications in their smartphone, right? So in smartphone, what we have? How the smartphone is monitoring my health? How it is possible to build any health monitoring application
using
with the
sensors.
smartphone? Right. So in smartphone we have a very rich array of sensors: accelerometer, gyroscope, magnetometer, GPS, many sensors, right? So accelerometer sensors, gyroscope, by combination of different sensors, we can build an application and monitor the activity of a human activity recognition, right? Once you monitor the human activity, this smartphone will be able to monitor the pattern of that user. মানে এখন হাঁটছে, এখন বসে আছে, এখন দৌড়াচ্ছে, এখন ঘুমাচ্ছে, all these things. I mean, if the phone is in his or her hand, right? So if you have the activity application, it is actually continuous generation of data. You need to store that data somewhere. You need to analyze that data to infer the knowledge, whether what is the activity of that user at that moment of time. So you need to store the data in the cloud. So you need cloud. Then to infer the knowledge out of that data, you need to run any AI model there. Any machine learning, deep learning model. You need to train that, so you need AI. So when you have all those things and you get that this is the pattern of that particular person, so personalized recommendation you can generate. So that personal recommendation you may want to provide to that user. How will you give? You need a mobile app or web app for that. So you need a fair idea of all those components to understand this field and to build an application or as an engineer to solve any problem. Is that good? Any other question? Okay, thank you.
compute services of AWS platform. So first, let me know how many of you already heard about compute services of AWS. Okay, and did you use that?
No.
Fine. So compute services refers to those services that help us to run applications and computing tasks in cloud. But before going into the details of those compute services, we'll first discuss about different platforms, computing platforms that provide those services. Now, there are three leading cloud computing platforms that are very popular, namely AWS, Amazon Web Service, Microsoft Azure, and Google Cloud Platform, that is GCP. Now, among these three, AWS is the largest and most widely adopted cloud computing platform because they actually acquired around 32% of the market share, which is followed by 22% of Microsoft Azure and 11% of GCP. And if you just combine these three, then it will be around 65%. And you can guess why these three platforms are actually dominating over others. And next, here you can see the recent trend of the popularity of these three platforms. The graph basically shows how the popularity increases day by day. And you can see clear increasing trend. But today we will mainly focus on Amazon Web Service. We will not focus on GCP and Azure and all. So now AWS provides different categories of cloud services like compute service, where user can run their applications and computation tasks in cloud, storage service like cloud storage as a solution. Some examples like S3, simple storage service, and about EBS, and some database services like DynamoDB and RDS. There are other AWS services like container management system, Internet of Things, and machine learning services are there. But today we'll focus on the compute service, and under compute service, AWS provides different services like Amazon EC2, which is Elastic Compute Cloud, and you require that service when you want to run servers, virtual servers. Similarly, we have AWS Lambda, which is basically a serverless computing solution. AWS Elastic Beanstalk, which is used for scaling and kind of load balancing tasks. And we also have like Amazon Lightcell, which is very simple solution that is used for easily launch and manage some virtual servers. Now here, as I have said, we'll mainly focus on compute service, but under compute service we'll explain the Amazon EC2 Elastic Compute Cloud part, and we'll do some explain some hands-on also. Now let's start with the basics of EC2. So now, first thing is, what is EC2? Suppose you need a computer. So instead of buying a new physical computer, you can just get a virtual computer, virtual server in cloud, and that's what EC2 is. So it's like a way to have your computer on the internet, and that's why it actually comes under the category of infrastructure as a service. Now, before we proceed, we'll just understand some important terminologies in EC2. Let's start with the instances. Instances basically, you can think think it as a virtual server or virtual computer. And when you need a virtual server, you basically launch an instance. There are different instance types for different hardware configurations of CPU, memory, storage, and etc. An example is the Amazon T2.nano instance, which is having one virtual CPU, 0.5 gigabyte of memory, and EBS only storage, and low network performance. So you can note that EBS is basically here nothing but storage volume which come with EC2 instances, and it can be of different types like your SSD or HDD. Now, there are naming conventions associated with EC2 instances, instance type. For example, in case of T2.nano, the T is basically the instance class, and 2 is the generation, and nano is the size. A size basically refers to different combination of memory, storage, etc. Now, there are different other instance types like this. And there are actually different classes. You can see class T, class M, class C. So those classes are actually can be segregated into different use cases like general purpose, compute optimized, memory optimized, storage optimized applications. Now we have another terminology called AMI, Amazon Machine Image, which is basically a template that contains software configuration of that is required to launch an instance. And AMI basically save time by starting with already pre-installed software setup. And the key components of AMI is the different operating systems along with their additional programs like SQL Server, PyTorch, TensorFlow, etc. Now, AWS is distributed across different regions and availability zones and here the region is basically representing a separate geographic area, and for each region we found different multiple isolated locations which are known as availability zones, and under each availability zone we have a group of data centers like this. Here in this example we have one region having 3 availability zones, and for each availability zone you have some data centers, and you can see the availability zones are actually physically isolated, but they are interconnected with networks, and for each availability zone we can have as for each region we can have a minimum of 2 availability zones and maximum of 6 availability zones, but usually there are around 3 availability zones per region. Now, here is a list of existing regions and availability zones. You can see, for example, in case of US East 1, that is North America region, we have 5 availability zones like US East 1A, 1B, and like this. Similarly, in case of Asia Pacific, that is AP South 1 region, that is the Mumbai region, we have 2 availability zones like AP South 1A and AP South 1B. Now, we also have security groups. Security group basically used for network security in AWS, and it is it actually filters the inbound and outbound traffic, and you can think of it as a firewall. They control how traffic is allowed into and out of the EC2 instances. They basically provide a secure environment for your resources like EC2. Now here we'll give you some bits of hands-on details. So first we create a EC2 instance, then we connect to that instance using EC2 Connect, and then we work with that instance a little bit. So these are the broad steps. First we open the EC2 dashboard, EC2 Linux instance by choosing AMI, instance type, basic, and then configure basic instance details, add security groups and all, and then we connect to that instance, and then we work with the instance. So first we need to go to the Amazon console, then we have to click on My Account, then you have to choose AWS Management Console and log in. Then you will find that all services, by clicking all service, you will find all the services provided by AWS. But here we will concentrate on the compute service, and under compute service you will get EC2. If you click on EC2, then you will find the EC2 dashboard. You can see here we have the North Virginia region, but you can choose any other regions also. And under North Virginia we have these resources. For example, here we have already one instance, and currently the instance is not running. So if you want to see what are the existing instances, you can just click on the instance, and then you will end up in a page like this. So here you can see we have existing instance called and in that instance we have instance like ec.medium, and it is created under the availability zone US East 1B, and currently the instance is stopped. So if you want to create a new instance, then you have to just click on the launch instance, and then you have to provide the name of the instance. For example, here I give the name FTP AWS. Then you have to just scroll down and choose the AMI that I have already said. So here you can have different options of OS. We choose Amazon Linux because it is under free tier, but you can choose any one of any like Mac OS or whatever you want. Next, you have to select the instance type. So here our instance type is t2.nano, but here also you can select other instance type that like t2. Here we choose t2.micro, but you can choose other instance type like t2.nano or t2.small. Next, you can create a new key pair. So the concept of new key pair is basically like private public key. Here, if you click on create new pair, then you have to just give a name of the key, and then it will give you a key pair that you can download. But actually, this key is the private key, and the instance will keep the public key part. And if you want to access that instance through AWS CLI, then you need that key. But we are actually using EC2 Connect, and that's why you don't need that. But I show the procedure here. Next, you can change the network settings, but actually decided to go with the default one. Here, anywhere is field is all zeros. It means that any inbound cloud will be allowed. Now, you can configure the storage. Here I took 8 GB of memory, and then you can launch your instance. And you can see that it is launching, the instance is now launching, and after that, after a minute or two, you can get a success message. And then, if you go back to your instance page, you can see that you get a new instance called FTP AWS, and currently the status is initializing, but after 10 minutes or 10 to 15 minutes, the status will be ready, changed to ready, and then if you want to connect to your instance, you can click on action and then choose connect. Then there are different options. So if you select EC2 instance connect, and then click on connect, you get a terminal like this. Here you can do anything that you do with your local Linux terminal. So for example, you can try with some, I have tried with some basic Linux command like clear to clear the screen, then who am I, then create a directory, then ls them. So you can do anything that you want. Now you can, if you want to see similar videos on GCP, you can follow our YouTube channel, and you will find a detailed video on there.
So now if you have any question, you can ask Mr. Asif directly.
The virtual machine that has been created in AWS, what will be its IP address?
Yeah, actually, let me show you. Here,
No.
under networking part, you will see the public IP address. Actually, currently the security is click. So if you click on networking part, then you will get that details like DNS, public address, all this.
That ID will be the ID of the device for which this machine is being created. So it will be a different one.
The public ID will be different one. Suppose you want to access that instance from your local machine, then you have to actually, I showed you a key pair, right? So when you are inserting the key pair, you are authenticating yourself, and then you have to provide the public ID of the instance, not your local machine. Then only you can connect to that instance and work.
Okay, so throughout the sessions, ma'am has provided knowledge on various things from the very basic to different types of cloud infrastructure. Okay, sir, please continue.
So he is shown up energy, we will talk about the research work then.
अरे छोड़ो ना
Okay, good afternoon, everyone. First of all, I'd like to thank Madam and AICTE for such a nice discussion on cloud. Actually, this will lay the foundation for all of you to understand the essence in research areas of cloud and this thing. So, you all might have, might have understood that cloud itself is a complex architecture. So, it's constantly evolving. So, research in this area requires to be followed regularly. Coming to the taxonomy of research areas, it can broadly be classified into these sections like cloud architecture, resource management in cloud, data management, interoperability and portability, security part, modeling and simulation part, application domains, and other engineering and management parts. So basically, we have some conclusion on resource management part. So let me just quickly touch upon the resources in cloud, as Madam has already briefed you on this. That is, broadly the resources can be classified into these three sections, that is compute resources, storage resources, and network resources. The compute resources are nothing but related to the processing power of cloud, that is virtual machines, containers, etc. And storage resources are like databases or the memory, you can say, this file storage and other object storages. A network part is nothing but the virtual network, load balancer, and all the networking parts. Now, before jumping into the details of our contribution, let me quickly show you the flow of virtual machine request in a typical cloud data center. So it all starts by generating virtual machine requests from users. So once the user requests a particular virtual machine, it associates with various resource specifications like the amount of CPU requires, the amount of memory it requires, and the amount of bandwidth it requires, and then it undergoes an analysis part where the system checks if the amount of resources that it is requested is available in that system or not. If the resource is available, then the resource is getting allocated to that virtual machine. If the resource is not available in a system, then it may be queued or the request may be rejected. So once the VM request has been granted by the system, it is the virtual machine placement module has been called upon, where actually the hypervisor part is there. The hypervisor that I have already talked about. The hypervisor actually takes in charge in place of VM placement module, where the hypervisor thing, the software actually places the virtual machine on top of that server rack, so on top of the physical machines. So this is actually the flow of the virtual machine. Once the virtual machine, the work of the virtual machine is over, the resource from that virtual machine has been taken to service queue. Now there are some interesting observations that led us to the to do our research in resource management cloud. There is the picture actually depicts here the requested CPU versus the actual usage of CPU of one of the publicly available well-known cloud trace, that is one of the big branch trace. So in the picture clearly depicts that there is a significant gap in between the requested CPU and the actual usage, actually used CPU. That means you can clearly see that the CPU request varies from a number of 3 to 4. That means users actually demanding for 3 to 4 cores of CPUs, but they are actually using less than 1 core of CPU. So there is a significant gap in between the usage. What it actually means that the resources are actually wasted. So if we try to predict that actual usage of the CPU from their historical data, and accordingly if we can allocate those resources, then we can minimize the gap in between those lines, right? So these are the same observations that I have just talked about. And one more thing is that there is a significant fluctuations in both the CPU usages and as well as the CPU request. And this is not the true for CPU. In case of any other resources like memory or bandwidth utilization, we have seen the same kind of trend. And this is not only true for big trace based, also there are many publicly available databases like GCP trace, Google Cloud Cluster trace, actually Alibaba trace, and Panac trace. In all those traces, we have seen this kind of similarities. So, the first observation is dynamic workload changes. So, as shown in this picture, that there is a significant fluctuation in the resource usages. And another one is another important point is this SL impact, that dynamic changes in workload results in increased SL evaluation. So, SL evaluation is nothing but related to the quality of service of the data. So, if we are trying to allocate virtual machines based on the requested CPU, then we will actually ended up with deploying more number of physical machines than their actual requirement, which results in increasing the energy consumption of the overall data center, and as well as impacts the SL. Okay, so the next one is the server behavior energy consumption that I have already talked. I'm not going into the details of it. So these are the key imperatives for cloud resource management. First one is automation efficiency, SL optimization, server efficiency, adaptability to cloud dynamics, and advanced analytics and monitoring. And these are the popularly the cloud resource management policies can be categorized into these 4 sections. Actually, these are nothing but the objectives around which the current research trends in cloud evolving. So we'll talk them later on this slide. So these are basically the algorithmic approaches in cloud resource management. These approaches can be categorized into 4 broad sections like heuristic algorithms, meta-heuristic algorithms, mathematical programming, as well as machine learning algorithms. So heuristic algorithms are nothing but the basic like rule of thumb kind of approach, right? So like best fit decreasing or the first fit decreasing, these kind of approaches are categorized under heuristic algorithms. Next one is meta-heuristic algorithms, which are kind of high-level strategy for optimization, like genetic algorithm, particle swarm optimization, simulated annealing. These kind of algorithms fall under meta-heuristic algorithm. Next one is mathematical programming, like linear programming or linear integer programming. This kind of optimization fall under mathematical programming. And the last one is machine learning algorithms. Like it employs the predictive analytics part. These kind of algorithms fall under machine learning algorithms. So this is one of our work that has been published in the Journal of Supercomputing. The title of the paper is Efficient Resource Utilization Using Multi-Step Ahead Workload Prediction Technique in Cloud. So the objective basically is to, the objective is clear, as we have seen in this picture that there is a significant gap, right, between these 2 lines. We want to minimize that gap. That means we want to build a predictive model that can predict the actual usage of the resources. So that is the main objective of this paper. That is the allocate resources based on actual virtual machine needs. And for that we have the basic approaches is to we have to build a predictive model, and based on that prediction we are going to place the virtual machines or allocate the resources to the virtual machines. And There are various challenges that we faced while
Go back to
research.
the title of this page. Yeah.
So there are several challenges that we faced while doing this research. First one is it is very much difficult to model each virtual machine usage pattern. Like for example, different virtual machines have different needs. So if we try to build a generic predictive model for all the virtual machines, then it is quite difficult to get such a model because we are not able to capture the heterogeneity in the application running on the virtual machine. So in order to capture the heterogeneity, we have to first categorize the virtual machines into similar groups or similar type of clusters. That is why we have to, first of all, we have to build a workload categorization model. That means we have to cluster similar type of virtual machines into similar categories. And for that, we have utilized agglomerative hierarchical clustering. It is it actually nested hierarchy. It actually represents a nested hierarchy of similar type of objects, and it is pretty common in these kind of scenarios. And one more thing which is important about agglomerative hierarchical clustering is that it is you don't need to provide any kind of additional parameters for it. Like in case of K-means algorithms, you have to provide the number of clusters by yourself. Like you have to provide the value of K. But in case of agglomerative hierarchical clustering, you don't need to provide this kind of parameters. So this is one of the advantages of this AICTE algorithm. And like all other clustering algorithms, there requires similarity measures based on which the clustering algorithm takes place. So in this case, we are actually utilizing dynamic time-lapsing method. So actually, you might have understood by now that those relationship patterns actually are time series by nature. That means these are sequence of data plotted with respect to time. So in order to get the similarity between time series data, dynamic time-lapsing method is quite popular. Because it actually captures the shape between those two data, those two time series data. That is why we are utilizing dynamic time-lapsing method as a similarity measure for the clustering algorithm. Now, once the clustering has been done, there is another problem we face. That is, if we want to build machine learning, let me first of all explain why we need to do this kind of predictive model based on machine learning algorithms. Because time series, there are various time series, traditional time series forecasting models available in the market, like agglomerative, auto-regressive, moving average, ARIMA model, auto-regressive integrated moving average. These kind of predictive models are already available in the market in order to predict the forecasting of time series data. But these kind of models are basically based on linearity of the data. That means they are not able to capture properly the non-linearity present in the data. That means the fluctuation present in the data, they are not able to capture coefficiently. That is why we are moving to machine learning algorithms. But there is one problem that we face while using machine learning algorithms. That is, the time series data is a one-dimensional. You can think of it as a 1D array. But in case of machine learning algorithms, they are used to train on a data set that is having two types of data, that is independent variables and dependent variables. So we have to first convert the time series data into a supervised learning problem model. And basically we are utilizing the supervised learning algorithms like linear regression, KNN, NEP-Centric, support vector machine, this kind of algorithms utilized. So for that conversion, we have utilized another concept that is known as sliding window method. Let me just show the concept. So sliding window concept is nothing but it is a time series data. So we specify a fixed segment of data that is known as a observation window. You can think of it like that, observation window. So we first of all we select that the fixed interval of the segment, that is the observation window, and we each time we slide that window by one time step, and we go on continuously doing the same process for the entire data. And as a result of which we are going to get data that is structured similar to the structure of machine learning algorithms that are familiar to work with. Okay. So this is how we place the sliding
What
window
problem
concept.
you are exactly trying to,
Sorry?
figure out and solve? What is the exact problem you are trying to figure out and solve? What are the features? You are using machine learning models.
Machine learning models.
What are the features?
Features actually, it is actually a time series model. So you are having the CPU usage or the resource usage for every time, right? If you want to run the machine learning models,
RNN model or variants of some RNN model, you could have used that also.
we could have used that, but in those scenarios, we have to train our data set, right? We have to train the model using the data set that is separated between independent variables and dependent variables, right? But in case of time series data, you cannot view that data like those data sets. So you have to convert the time series model into this kind of data set, right? Because you can think of it as an array of data, time series data as an array of data, and you have to convert that array of data from a matrix of data. That is because machine learning algorithms are trained on that data, that matrix form of data. So the work here is to convert that array of data into a matrix form. That is why we have replaced that sliding window concept. Using that sliding window concept, we are converting that array of data into a matrix form. The single dimensional array of data into a matrix form. Into a 2D array, you can think of it.
So you can fit the single dimensional data also into a neural model.
We can do that thing, but actually that might have a time consuming process.
But you need to, it is overhead when you are taking that vector and then you are making it in a matrix.
Yeah.
So it will take some extra time.
Extra time,
Where
but
you
that
can
is
directly
very
fit it
compared to
into the
training
neural model.
those highly computational neural networks. It will be much less computational intensive compared to that models.
So we have actually tried with the other models also, and the experimental experience that we have gained for this setup is that these things are less compute intensive or less complex in terms if you compare that
To that neural networks.
Yeah.
Usually,
And then the problem that you asked that what is the exact problem he is trying to solve here, because you can see that there is a demand of the CPU request or the spike in the request and the CPU usage. Mostly the requests are very high in respect to the actual usage. So from the service provider point of view, if you have a very nice prediction of the usage based on the request which is coming, if you have that, you can make a very nice policy for the utilization of the or the optimization of the resource utilization, right? So that is his main problem area, and then he has the access of some existing data set. Based on that, he explored, different time series models he explored along with this. And thing is, when you are trying to build some deep learning models, they are very complex. They are giving a very costly solution, right? So here the idea is to get a trade-off between the cost and performance and the experiment or experience that we have gathered from this set of things, that this kind of models are really working very good.
And also they are less time consuming. The linear regression, KNN, DT, the division tree, substitution, they are less time consuming compared to those difficult ANN models, right? So that is the main focus of our work actually, to reduce the time, to reduce the training time, these kind of things. This is the proposed framework of this model. Coming to the experimental setup, we have utilized deep brains data here, and we have designed a simulated platform based on Python, where we simulate the workloads of deep brain space, and a sequence of 350 hours of virtual machine resources has been placed in this simulation, out of which the training set consists of the first 300 hours, and the rest 50 hours, remaining 50 hours of the data has been used as testing purpose. And the experiments are performed on 100 Dell PowerEdge R65 series servers, and the performance, the information about the power consumption of the servers you can get online from spec power benchmark dataset, from where we are able to get that power, the load versus power result from that benchmark dataset. And the results clearly demonstrate that our proposed model significantly outperforms the conventional method. In that table, the last table, you can clearly see that the first row of the table shows that the average physical machine requirement, if we use the conventional method, conventional method means that we are going to place the virtual machine based on their requested resources. If we are going to follow that scenario, then we are getting only about 80 physical machines. But if we place the virtual machine based on their actual usage, then the CPU requirement reduced to 80 to 16. There is a significant improvement within this, right? And also, in case of CPU consumption, actually we are utilizing CPU and memory in this particular experiment. In case of CPU, the virtual machine has been clustered into 3 sections, and in case of memory, the virtual machine has been categorized into 2 clusters. And for CPU consumption, for the first cluster, gradient boosting performed very well, and for cluster 2, dynamic recently performed well. For cluster 3, support vector machine performed well. Similarly, in case of memory consumption, for cluster 1, support vector machine consumption, and in case of cluster 2, gradient boosting performed well. This is another work of us on this particular domain, that is SLA or stochastic load balancing in dynamic cloud environment. So, as the name suggests, the work is basically on load balancing in cloud. So, the basic concept here is that there is a trade-off between the user's perspective and the service provider perspective. There is a trade-off. Like users want to run their virtual machines in a lightly loaded host, so as to complete the whole task as early as possible, so as to experience the seamless experience. But on the other side, cloud service providers want to run those virtual machines in such a manner that it requires less number of physical machines to run them. That means they want to pack the virtual machine as close as possible. So there is a trade-off between both these aspects. So we have to identify, we have already identified that trade-off, and we want to propose a solution accordingly. So in this work, we are actually utilizing multi-thinking approach in order to solve this problem. Basically, actually, load balancing problem requires to address 3 main questions. That is, when to migrate a virtual machine, which virtual machine to migrate, and where to migrate the virtual machine. So the first question is pretty straightforward: when to migrate the virtual machine, right? So whenever you see a load imbalance in your system in the cloud environment, that moment you need to migrate the virtual machine. That means if one or more servers is getting overloaded, that moment you want to pull out some of the virtual machines from that physical machine and then want to migrate it from some other physical machine, right? So that is the question for, that is the answer for when to migrate the virtual machine. That means whenever there is a system overloading happens in the system, you need to migrate the virtual machine. Next question is which virtual machine to migrate. So we have to specifically choose the specific type of virtual machines from the overloaded physical machine. That means if we randomly pick up a virtual machines from the overloaded server, then it might not work well in other scenario. For example, let's say a physical machine is getting CPU overloaded. That means their CPU request is getting more than their actual CPU capacity. So if we, in that scenario, if we try to pull out a virtual machine that is memory intensive in nature, then it might not lead to a good solution, because in that case the number of migration might increase, and as a result of it the performance of the system degrades. So in that scenario, what we can do is that we have to pull out the virtual machine from the physical machine that is CPU intensive in nature actually. In that way, we are actually reducing the number of migrations, and as a result of which the performance degradation actually lowers. Okay. And next one is where to migrate the virtual machine. So after pulling out the virtual machines, if we have to place we have to understand where to place the virtual machine. So let's say we pull out a virtual machine that is CPU in nature. So we have to select a destination physical machine or destination server for that virtual machine that has ample amount of CPU to accommodate the virtual machine. Otherwise, it might not be possible. Otherwise, it might not be possible. Otherwise, there might be a chance of future load imbalances actually. Okay. So we have to basically address these three questions in case of system overloading or cloud overloading. So this is the architecture of our proposed one. Here we are actually utilizing a stochastic prediction model where to identify the stochastic nature of the workload. We are utilizing a probabilistic method, and we are actually estimating the distribution parameters of the workload, that is the mean and standard deviation of the workloads, and based on which we are actually predicting the future usage of that resource. And after that prediction, the overload detection module has been called, which is constantly monitoring whether there is existing overload in the system or not. Once it detected the system overload, it triggers the next module, that is game selection module, and upon selecting the optimal number of virtual machines, it triggers the destination physical machine module, which then triggers as the actual migration through virtual machine management. Okay, so in order to select the migrating virtual machines, we are utilizing multi-criteria decision making approach, that is MCDM approach, and where we treated the virtual machine as alternative and resource type as criteria, and we place a linear scalarization method to assign weights for each of the resources, and based on that weights, we are actually prioritizing the virtual machines, that is which virtual machine to pull out from the overloaded system and overloaded host. And in case of selecting out the destination physical machines, we are actually utilizing the multi-criteria decision making approach itself, but instead of utilizing linear scalarization method, we are utilizing WSM method, that is weighted sum method, to get a weighted sum of that resource, which is known as the destination potential score for all that physical machine, and based on that score, we are actually placing those virtual machines. Coming to the experimental setup, in this work we are actually placed Planet Lab trace and Google Cluster trace to generate the virtual machine workloads. Here also we are building a simulated platform using Python, and simulated a heterogeneous data center with 1,000 physical machines that are hosting 8,000 virtual machines, and the simulation span with about 24 hours duration. And in that particular experiment, we are utilizing Hitachi AJ800 series, 8000 series, and Entry Korean email 110 series. These are two types of physical machines that are used in this experiment. And the experiment is compared with real, that is resource intensive or load balancing approach. One of the well-known approach that is in this particular domain. Another is Sandpiper, and another one is Cloud-Scaling. So the experimental results shows that the number of migration in both the traces, that is Planet trace and Google Cluster trace, the number of migration utilizing our approach significantly reduces compared to the other approaches. And in case of CPU utilization as well as memory utilization, it also shows that we are able to utilize those resources in a much better way compared to the other approaches. There is another paper of us which actually addresses the same problem, but the approach is in a different way. Instead of that means we are actually identifying that trade-off, and in order to solve that trade-off, we are utilizing game theory. Okay, so the objective actually is to find an optimal placement that utilizes all the resources maximally in a balanced way. The paper has been published in Platform 2022. I am not going into the details of this work. So this is the experimental section. Here we are considering three resources, CPU, memory, and disk. And we place HP 380 series for that simulation. And we are comparing using IRB VMP and Day3 design approach. It also shows that our closest approach outperforms all the others in terms of number of migration, number of physical machine deployment as well as deployment. Now there are other results in this field like cloud federation. And the cloud federation, ma'am has already described about cloud federation, that is, it is interconnected cloud computing environment of two or more cloud providers integrated together to allow portability of data and applications. So these are the key result areas in cloud federation: portability, privacy and security, automation, incentives, service level agreements, and legal training. These are some of the possibilities and challenges in cloud federation. Another aspect is the data offloading in fog and edge computing. So fog and edge is nothing but the intermediate nodes between you and cloud. They are like there are switches, there are servers. So these are the edge devices. You can think of them as edge devices. So there are various recent trends actually shifted towards data offloading in fog and edge computing. There are various aspects nowadays in those areas like workload and resource allocation algorithms, incentive, patterns and mobility support. In my session, if you have any questions.
Okay, so if you have any questions, you can directly ask Mr. Shona. I think no more questions. So the overall the session is very interactive and very informative. So thank you, ma'am. Throughout the sessions we got very basic idea of cloud infrastructure, as well as you have discussed many things, and at the end we got some fundamental idea of how to configure a cloud, and later Mr. Shona have discussed what the research topics are there and what are the different challenges are there. So I think this knowledge will help us many work in the future. So thanks again. Now I'd like to request our principal sir to kindly hand over the small token of appreciation to ma'am. I also request sir to hand over small token of appreciation to Mr. Ashit and Mr. Shonak. So sir, please come. Finally, I would like to thank all of you present here for taking the time to be with us today and helping us make this event a grand success. So thank you all. Okay, there is a small announcement. The feedback form was already sent to your mail ID. So kindly fill this feedback form.
All participants, there will be lab session as usual.
আমাকে না অ্যাটেন্ডেন্স দিতে হবে, সপ্তাহে স্টুডেন্টকে অ্যাটেন্ডেন্স দিতে হবে।
ল্যাব পরীক্ষা,
হ্যাঁ হ্যাঁ
ল্যাব পরীক্ষার অ্যাটেন্ডেন্স।
হ্যাঁ
সব খোলা পড়ে আছে, ভলেন্টিয়ার্সও নেই, স্যারের ল্যাপটপ প্রজেক্টর ওয়াইফাই কেউ হ্যাঁ আমি সৌরভ নাক স্যারকে পাঠাচ্ছি চাবি দিয়ে।
এটা বন্ধ হয়েছে?